Hello everyone, welcome to week 12 of Grasshopper, and in this week we're going to look at a plugin called Kangaroo. It is a physics simulation engine, and there's some description down here, but essentially Kangaroo works and simulates the physical behavior of particles. And particles, the forces that work between particles, like springs, gravity, drag, these sorts of things. Although in our case, we're specifically going to be looking at springs and gravity. And because of that, you're able to simulate a large variety of physical behavior. In particular, in our case, catenary curves and essentially these sort of force loading structures. So we'll take a look at that in particular, and if you look at the Food for Rhino website where the plugin is hosted, it's a Kangaroo. And one thing to note is that most of our content right now is focused on the, basically the 1.0. This is very close, but Kangaroo version 1. And that's the version we'll be using for most of the stuff and the examples. Now, Kangaroo 2.0, which is a complete rewrite, was just released not too long ago, and next week we'll see some examples of those, except this is actually fairly new, and the way the components are put together are a little bit different. So they are not at this point cross-compatible. All right. Now this week we're basically going to look at two approaches. One, which is this series. If you can look at essentially our example files down later on, essentially 1 to 3 are based off of creating your own Rhino curves to create point networks that Kangaroo can work with. And then 4 through 7 are based off of essentially using the inherent quality of meshes and all of their intersection points, or the mesh points, because you can get a very dense mesh network and use those to simulate. So 1, 2, 3, these 3 are basically all working with curves, or some version of generating Rhino geometry and subdividing it to get a lot of points. The 4, 5, 6, and 7 basically work off of some mesh that you create, or a mesh that you can basically make from something else, right? So in particular, actually, 5, 6, and 7 are basically the same thing, except more complicated. So you'll see 5 and then 6 just extends it more, and then 7 actually extends it more. So 5 is the basic, 6 adds holes to it, and then 7 adds unfolding and fabrication logic to it. So it's not completely necessary. As you can see, it gets really long, but you can take a look and see what it does. Yeah. So these are the two approaches we're going to take. Now, in particular, I'm going to build from scratch, more or less, the first one. This is the Rhino file that I've provided in an example that you should use. It's called Kangaroo Catenary base.3dm for this week, and all of the geometry that is referenced in these example files are in here already, except they might be on a hidden layer, and these layers essentially correlate to one of the example definitions, right? So if we're looking at the first file, then this is the one, and you'll see that there are essentially 2 points here. There are 2 Rhino points here that are in the file. If I hide them, and then you're starting to work with the next definition, then show that layer, number 3, number 4, number 5, and 6. Okay, so that's just the way you can kind of tell which file eventually we're working with. All right. So because we're working with number 1, these are the 2 input points. And I'm going to go to Kangaroo. So Kangaroo is this. This is Kangaroo 2, which if you install it, it will come in by itself, so it's separate. Kangaroo, the normal Kangaroo, is installed by going to File, or the Grasshopper menu, File, Special Folders, Components folder, basically, and there are two files, a GHA file and a DLL file, and just basically drag and drop these two files into this folder and you're done. So you'll see these here. Okay, and that's it. You might have to unload Grasshopper by typing, I usually just type unload and click on this, Grasshopper unload plugin, and then load Grasshopper again. And then it will read Kangaroo correctly if this is the first time you're installing this. Okay, so let me start by kind of describing these are all the forces that are available to you. This is the main Kangaroo solver, and these are sort of mesh utilities, and you'll see this is why we introduced Kangaroo with Weaverbird, is because Kangaroo is very good at utilizing meshes to do a lot of the calculations or simulations, and there are some tools between Kangaroo and between Weaverbird that have very good synergy. Some utilities that are useful, actually the remove duplicate points one in particular, remove duplicate lines sometimes, right? So, okay. Let's look at the main solver. This is what it looks like. These are the inputs, and we'll kind of go through these one by one. Now, in our this particular example, we're going to try to simulate a catenary, which is essentially basically what the shape of a hanging chain would take, given two fixed endpoints. So you can see the sort of physical versions, the mathematical or the force diagram of it, but essentially these catenary curves, if you reverse them, flip them upside down, they are essentially the most efficient loading path for a spanning structure, for that given spanning structure. So this is why structurally it's so interesting to architects and structural engineers and designers in general, the efficient spanning. And if you look at Gaudi and his hanging catenary chain models that he used to basically simulate, vaulting structures, which many examples you see in his work, including the Sagrada Familia and some of his other houses in Barcelona. Okay, so that's the sort of context for this. And so what we're going to do is basically simulate just one hanging chain. To do that, we'll have to look at two types of forces. Now, essentially because Kangaroo looks at force, and a hanging chain basically will have two forces. One is the force of gravity, and one is the force of the chain itself, the force that keeps, let's say, two segments on the chain together, right? So that's the spring part that we'll start to define. Now, because of that, we're going to look in the forces and see what we have. Now the gravity force isn't, described as gravity, but as a unit force, which means basically a uniform force, vector force acting on a point. And so we'll use this to simulate gravity. This can also be used to simulate a lot of other forces that are consistent in one direction. So this is going to be our gravity. And then the other force we're looking for, type of force we're looking for, is this one, springs from line. So this creates Hooke's law springs. Now if you don't remember the Hooke's law, the TLDR version of it is essentially it describes the behavior of springs in proportion to distance when, especially when the stiffness is a constant factor. It doesn't deal with when, let's say, a spring goes into destructive stretching or bends out of its normal state. Okay, so it all assumes that it can resume its normal length, right? All right, so that's Hooke's law springs. So these are the two forces we are dealing with. Now, so a chain has a lot of points, a lot of nodes, so we want to be able to give Grasshopper a lot of points that are in a line or in a chain. Now, given that you'll see that our two inputs are 2 points, then it's pretty easy to kind of infer that we are going to input these 2 points. So let's go to params, point, set multiple, and click 1, 2. So those are our points. Let's actually use those 2 points to draw a polyline, and connect it to the vertices. So here you'll see essentially we have, a line between the 2 points that we've inserted. Right? Simple enough. Let's take that line and divide it. Divide curve. And put in a slider, let's say 0 to 40. Or actually 50. And that's the number of subdivisions. This is the curve, and there. Okay. So now, if we start upping the subdivisions, then you'll see we're creating a lot of points on this line, and these are basically will represent each segment is, let's say, a link in the chain, or in our case it will become parts of the springs. They'll be simulated as springs. Alright, so now we know that actually we can actually use this already, because these points are what gravity will act on as it's, let's say, pulling up or down, right? If it's pulling downwards, then that's gravity. So these points, if you look at the inputs for the points, these are the points to apply the force to. So that goes into there. And so you see actually there's a vector representation of the direction the force is pulling right now. Right now it's actually going downwards -9.8, which is the gravity constant of acceleration, 9.8 meters per second squared, right? But we want to be able to adjust this, so I will actually give it a z vector, unit z vector, and also give it a multiplier. So in this multiplier, which is going to be the unitary force, I'm actually going to go into the negative as well. So -100 to 100. And this goes into there. So I can go from that to 100. Okay. Now, this actually is, and if you want to rename it, this actually is the unitary force. How strong it is and how it acts on these points eventually when we run the simulation. Okay? All right. Now the other part is the springs. Now to kind of describe this, essentially for the springs, the two right now that you have to care about is the connection and the rest length. All this other stuff is just kind of describing in more detail how how stiff it is, that sort of thing. Other aspects of the spring, but the two most critical ones that you must have is connection and rest length. Connection, essentially, if you hover over it, it says line connecting 2 points for the spring to act between. So it's actually just this. For each point, it's that segment that lies in between them. Rest length as well is basically its length while it is static or in its normal state, which is what it is right now in its normal state. So what we need to do is to be able to extract these short line segments, each of these little line segments. Now we could, kind of do the polyline again through all these points and then explode it and feed each line segment back in. That's doable, or that would work, but there is a shortcut basically called shatter, which will take a curve and break it down into, little line segments. If you kind of look at the icon for it, or the graphic icon for it, at specific t parameters, right? Or t parameters meaning, locations on the line, right? Addresses on the line. So what we can do is actually just feed it the polyline curve from here, which is this long line from here, And then with the t parameters, actually after we did the divide curve, it naturally gives us the t parameters as a list. So each of these points and where they are on the line as a number. So if we do that, this will actually give us, and I can start hiding this, this will actually give us all of these little lines in line segments. And you can take a look at this, you'll see essentially, I think 24 line-like curves because we're doing 25 subdivisions. Okay, that's it. So this actually will go into connection and rest length. Those are the two that we need. So from here on, we're actually going to start working with the Kangaroo object itself, Kangaroo solver itself. So it will require a couple of things. You don't have to worry about settings at first, although eventually you might get to that point. But the first thing we'll need is force objects. Now force objects means these two, the objects that are exerting force on whatever you're trying to simulate its movement on, right? So pull this, hold down shift to add this into it. Now this is actually the point that everyone forgets starting out, is that you must right click here and flatten it, because force objects have no hierarchy. All the forces are working on the particles at the same time, right? Gravity and the springs are reacting to the particles and what they want to do at the same time. There's no sequence. There's no, like, you don't apply gravity first and then the spring, or vice versa. So that's why this always basically is flattened. And this is really easy to forget when you're building something from scratch at first. Anchor points is easy because these are the points that remain fixed during the simulation unless moved by you, which actually means that endpoint and that endpoint. So we go back and it's our inputs from here. So that goes straight into anchor points, very straightforward. Now geometry can be a little bit trickier to understand, but this is the geometry that you want to move or change or transform. And in this case, it's not the line segments really, it's actually the particles that we want to move, or these sort of nodes that we want to see how they behave. So geometry in this case actually comes from here, the division points, these points that are being acted on upon. So that goes into there. The last one is simulation reset, which basically is a Boolean toggle, very simple. So type Boolean toggle, pull that into there. Now to complete the simulation, as you can see, I can actually do this. If I toggle it to true, false, nothing happens, right? So what we need to do is actually give Kangaroo a timer, because Kangaroo is a real-time simulation. It needs a timer object. So if you go, I think it's here under the param channel utilities timer, although I just generally just type time and put in a timer. Whoops. Timer object. And if you click on the arrow, it will have a dotted line that you can link to it. And that basically is tells Kangaroo, the Kangaroo solver, how frequently to update its solution. So this is, if you double click on it, it will gray out, which means the timer is off. If you double click that, then that means it's on. This is the solving interval. So if you see, if I click on the Boolean toggle, I have nothing going on right now because I haven't actually linked the out, or the result. So let's actually do that really quickly. And in this case, we can just really quickly, you can either use the particles, but in this case I'm just going to grab the geometry out, because these, if we look at this, these are essentially points, right? So let's do another polyline. Pull that in. And you can actually see the first iteration is being solved. And if I keep on if I toggle that, let's see, turn this on, then you see this is actually updating the solution at the speed of every second. If I want to speed it up, then you right click it on it and say, let's say 20 milliseconds, which will then update it much faster. Now, if you change the force direction or the amplitude of the force, then that will change, right, because of how much more force you're putting on it. If you move it into the reverse, then it becomes a hanging catenary chain. And this is the sort of reverse of what an arch ideally would be. And you can see that it will bounce back and forth. I'm actually going to close the unary force display because it's a little distracting, and hide all these so you can see that. Okay, so you can set this to a specific point or a specific value, and once it's reached equilibrium or stabilized, as you will, then you can essentially double click on the timer to freeze it. That freezes the solution without turning it off. If you click on the Boolean toggle again, it will revert back to its initial state, and then you have to start it again. And you have to turn on the timer, click on false to get it work. So basically it's working between these two. The one thing I suggest though is that don't save your file with the timer activated. Always save your file with the timer off, because if you try to open a Grasshopper file like this with the timer on, and if you have a very heavy simulation, sometimes it'll crash, sometimes it will take a long time for your simulation to run and actually. So this is basically the first example that you see in here, mostly basically the front part. And this latter part I'm not going to sort of deal with right now because this is more about visualization, but you can kind of take a look at applying colors and sort of tying the height of these tubes to the height of the geometry or a line segment, right? So that's not that's not the sort of main point of what we're doing this week. Now that's the main basic concept or idea behind how Kangaroo works with or calculates catenary arches. So given that basic premise, you can look at the two other examples that are associated with this. And in this point, I'm actually just going to pull these in. I would actually look at number 3 first, the surface tube, because it's more sort of in sequence. So I'm going to hide that, and I'm going to show the input geometry for this. And if I hide the Grasshopper display, basically it's these two curves on the ground, right? That's our input geometry. Bring back the Grasshopper. So instead of just drawing one curve, in this case we're using these two boundary curves, right? Input these in, dividing them. So you'll see a lot of division points on those, right? Taking that, and I can actually add more or less, so more or less, we can do less, which makes it do, like, let's say 15, right? Taking those points and then drawing a polyline between them. So each point has a section, and then basically doing, it's sort of transplanting what we just did earlier, the single lines, the single chain into each of these, right? Into all of them. So besides that, we're just replicating the whole process. It's just a different way of doing a lot of them at the same time. Okay, so all this is basically identical up to there. It gets, the only difference or tricky part is the anchor points here need to be flattened as well, because this is now a as you can see, the data is a multi layer or multi-tier tree data, right? So that's the only sort of difference you might run into in this regard. Okay, so you can take a look at this, but if I run it and simulate it, basically it does that. So The same thing, each one of these individual ones is identical to what we had earlier, except now it's doing it in a series. And the output is actually a lofted surface, where we take all the curves and just loft them together. And that's it. That's the only difference. In this definition. There's pretty clear annotation on this, so if any of these you're not quite sure what it's doing, you can read those. And as always, these are updatable in real time, so you can drag these around. Or if I chose to actually, let's see, rotate this, it's a little too much. And you'll see the simulation going crazy a little bit. It's pretty heavy, so I actually wouldn't do all of that too big of a modification. I'll force those on. So you can actually do things like this, drag the whole curve around, or if you wanted to, you could actually edit the curves points dynamically, and you'll see the simulation react, right? Same thing goes for this guy. If I change my anchor points, let me show the rhino. If I move my anchor points around, then you'll see, and because this is a single chain, so it's much faster in updating like that. Okay, all right. So let's look at the third and last example. I'm going to hide those. So this is the curve ring example. It's more or less the same idea, except this time we're taking a big curve, perimeter boundary curve, with a point in the center as the inputs. So imported point, this guy, imported curve, this guy. And you can swap the curve out for your own curve if you want. But the idea is that we're taking this, we're drawing a lot of lines, or subdividing the outside curve to draw a lot of lines inwards to this point, and then taking all these ribs or lines and then creating subdivision on them, and then drawing a lot of lines between them as well, right? So you'll see, take the curve, we'll subdivide the base ring, draw all of these in between lines, which is in this case it's called the spokes. Subdivide the spokes to get all these points on the spokes, right? And then use now you have all the points that you're using to kind of create unitary forces. One thing that's different here is actually, obviously, because remember, gravity acts on all the points at the same time. So there's a flange component here. There's a remove duplicate points component, because, for example, here at the center there would be 25 or however many points all overlapped in the same place, and effectively they're the same point. So because of that, this component is necessary to kind of remove overlapping points from the whole list, and then that's your gravity, which you feed in at the same time to the main Kangaroo solver, right? Okay. Other part is the springs, which is more or less the same, but you do have to graft it in this case to get the data structure to match up before you split them all into the tiny little segments, right? So both these and these, the ones that are transversal, the ones that are going the other direction, are basically put together into the same tree then considered as springs altogether. And that's fed back into force objects as well, which is flattened too. Okay? Anchor points, which includes all of these outside points on the very edge, and the center point, right? And that's what this merge component is doing. It's taking that center point and the subdivision points that's coming from the ring on the outside, putting them together into the same list and feeding them into the anchor points. And that's more or less it. This can look a little bit more complicated, but it's mostly dealing with data structure. Although otherwise, the main principle is the same. And what you get is this. Right? And this is a sort of polyline mesh of some curves that are going horizontal and some that are going vertical. And as always, that center point you can move and the solution will update. Right? Okay, so this is basically simultaneously simulating all these arches, but also the sort of horizontal connections between the arches, as if these were all springs. So it's more membranous behavior, tensile membrane behavior. All right, so that's it for this sort of first series of kangaroo examples from catenary examples, from 1 to 3. And in the next video, I'm actually going to go into basically four, but talk a little bit about the others as well.